as I had mentioned yesterday, we will discuss about code generation. And what we'll do is primarily talk about two specific code generators, one of a very simple kind and another that is somewhat more optimized, more advanced, but still a simple one. So let me share that. What is that? Is it visible?
Yes, sir.
Okay. So we'll first discuss about some key issues in code generation, and then some samples of generated code and two simple code generators. So in terms of code generation, we have so far done the generation of the intermediate representation, intermediate code. We have optimized it in several ways. And based on that optimized intermediate code, we have done a, let's say, some tentative register allocation, which may be intermixed with the instruction scheduling. The main issue of code generation are two. One is given this quads control flow graph and symbol table of symbol information. For every instruction, we need to choose the proper sequence of instructions in the binary or assembly language to represent it. And for that, we need to decide about the binding of every variable. That is, a variable could be in register for which we are doing the allocation, and if it is not possible, then whether we can have a register in memory and operate, it depends on the machine model. And in that choice, we will often see that there are multiple ways to generate the assembly for a particular 3-address instruction. A simple example here is if I have a quad A assigned A plus 1, then if my processor supports an increment instruction, then this could simply be coded as increment A. Or it could be coded as, translated as a normal binary addition where I load A into a register R1, add 1 to R1, and store R1 back to A. So naturally, you can see the first sequence will be faster than the other sequence. And normally, in terms of estimating this, what is faster and what is slower, we will typically use a cost estimate of 2 units for every load and store, because they would be 2 words long, and 1 unit for a register operation like add. Now, naturally, it is always important to consider what is the order of the instruction generation, because some may use fewer registers or maybe faster. Then which registers to use, the basic assignment problem. Whether to optimize for memory, time, or power. What we'll primarily demonstrate here is mostly focused on time, but equivalent heuristics could be built for memory or power as well. Another issue which you must keep in mind that often code generators are designed with retargetability in mind. Because when we write a compiler, we often would need to target it to multiple different processors. I could target it for an x86 32-bit architecture processor or a 64-bit one, some which may have a coprocessor. If I target it to some alpha processor or an AMD processor, it might be different and so on. Now, naturally, we would like to write the code generator in a way so that if I can provide the code generator with the basic information of instructions, their costs and capabilities, we should be able to use the same algorithm to generate the code for the specific processor. Right? So retargetability is important. Otherwise, for every processor, we will have to write this part of the backend separately. So that's what this means, that can the code generator be produced automatically from the specification of the machine. The specification of the machine is the available registers, addressing modes, the instructions, their costs, and if there are constraints on certain register use and so on. So if we can describe that specification in a certain form and let the code generator use that specification as an input, additional input besides the quad and the control flow graph and the symbol table, then we should be able to automatically generate the code generator. Right? So those are the basic issues. Now, let's start simple. I had talked about this briefly earlier, but let me just formalize it here. Naturally, it is more obvious if we are just doing arithmetic operations or condition check kind of. So here I illustrate what do we do for an array operator. So when I have an array operation, B assigned AI, so we will need to, now naturally, A from the symbol table, I will know that what is the size of the element. So depending on the size of the element, those many bytes will have to be read, which are having an offset of I elements from the base address A, and stored that into B. So we first load I into a register, which is basically as if I is assigned to R1. Then we multiply it by the size of the element, which here I have assumed is 4. So R1 multiplied by R2 is again stored in R1, assuming that A is 4 bytes long. Then we load A R1, which is offsetted from A by the amount computed in R1, which is the offset in number of bytes. The parentheses here mean that we have to take the content of that address. So we are dereferencing here and load that into R2, and then finally store R2, which is the value of AI, into B. So this is a simple code sequence which would represent, which would be the translation for A, B assigned AI. Similarly, if the array is on the left-hand side, we'll have to do something similar. Load Y into R1. Similarly, load J into R2. Multiply by the size in R2. And then finally store R1, which is Y, into X R2, which is XJ. For a pointer dereferencing, we can do the same thing. Load the pointer. And the pointer itself is the value it is pointing to. So we will assume that symbolically as a base address 0 with offset R1, and take that content and load it to R2, then load it, store it back to X. Similarly, the next one, if we have a condition check, X less than Y go to L, then you have to load X and Y into two registers, R1 and R2. Compare the registers, which gives you less than, greater than kind of status flags in the status registers. And based on that, we'll do a jump here. I have used a branch less than jump instruction to L for realizing this code. So these are some of the sample ways the code can be generated. Now, let us present a very simple scheme which we can illustrate and use for say is a kind of a macro based scheme where every quad is thought of as a macro which expands depending on the particular form of the quad, which expands to predefined code sequence in the target processor. So say the code is A assigned B plus C, which is the common generic form that you have a binary operator. Then one option, one macro could be you load B and C into R1, R2, add R2 to R1. So actually the value of B is lost now. It represents the value of A, and then finally you store R1 to A. Or you can directly, if your processor supports direct memory operation in the ALU, then we can load the B into R1, add C directly into R1. Again, B is lost here. R1 now represents A, and then store R1 back to A. Now, you will understand that when we do a sequence of computation in the quad array, we will often use the values that have been recently defined, or we may be continuing to use a particular variable multiple times. So this kind of a macro-based code generation will often result in inefficient code. We'll have repeated load and store registers, but the good side is it is very easy to implement. For example, when you are implementing your code generator, this could be a simple scheme that you can implement easily. So to take an example of what we have already done. So this is a 3-address code for the bubble sort. Of course, I will not go through the entire details. This is given here for you to work out and understand even more clearly. So this on the middle bottom here is the actual code in C, and I have tentatively followed the translation syntax directed translation scheme that we have discussed in earlier modules. Professor Mitro have explained in detail. So with that, we generate this code sequence on the left. And I have arbitrarily assumed that it starts at array address, quad array address 100. Take it in. And by the side of the address, I have marked asterisks in some places. As you can figure out, these are your leaders in terms of the basic block generation in terms of the control flow graph. So based on that, I generate the control flow graph here, where you initialize I to 0. Then primarily you compute n-1 and do the check. Based on that, you decide whether you should be terminating the whole loop and go to B3, which is this return, finally to B12, or you will have to continue with the loop. So here you have the initialization initialization for doing this comparison, and then based on this you could either continue in the inner loop or terminate the inner loop and go out. So this is a loop here and here. So you can see some of the blocks are big, and some of the optimizations I've already issued, like your multiplying by 4 realized by left shift and so on. So these are basic 3 address code that and the CFG you have. So kind of this is your input to the code generator. Going to the next slide. On this, the intermediate steps, again, I have not shown. You can work them out based on that code. But what I have done is I've done a 3 address optimization by peephole. I've done local shortened and global common sub-expression elimination by DFA. So with these, all of these get significantly shortened. And finally, the live variables are computed. And based on that, the global register allocation using Shettin's algorithm has been done. So now if you see that I have assumed that we are using 6 registers. And because we are using 6 registers, there are some variables which will get spilled, like I gets spilled. So every time we are using I, we have to load it here, 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 because this has been spilled. Similarly, your T0 has been spilled. And so with that, with 6 registers, we can have a total global allocation. T0 and I have been spilled. Only ARR is live, which is the array, of course. That is the big thing. So, so ARR is live everywhere. So actually, at every point, you should show that it is live. Just for simplicity in the diagram, I have not shown, but please keep in mind that the array ARR is live at every point, and that is what is allocated R1. And then the rest of the allocations, and at every point you can check, at every point you have the different variables which are live, based on which this register allocation has been done. And you have a couple of load store for I and T0 which are present here. Now, if you go with this allocation of registers, next what you do is based on this allocation, you replace the variables by registers. So it is like the previous code, but now you have everything written in terms of the registers, the 6 registers that you have. So this gets, almost like your assembly instruction. Only thing different is it is written in the notation of the quad, but you will have exactly almost 1-to-1 macro mapping to the instructions that you are using here. So this is the code that you get generated. So for example, R5, which was here we had I, so that is repressed by R5, and R5 is set to 0, and then it is stored to, because I had been spelled, so that is stored to IA, address of I, and so on. This is a long workout, so you will have to work this kind of things out at home, and see that you are you are comfortable in terms of generating the code here. I'm just showing a very, even with this first scheme, which is macro based and straightforward, you have 2 things. One is it is simple and gives you a code quite quickly and in a straightforward manner. But at the same time, it is with little bit of tweaking, it can be, somewhat good. I mean, it's not always that it's a very sloppy code, because here I'm assumed that we are doing a global register allocation before doing the scheduling. Right? Now, I could manage to do that because here I'm not looking at optimizations which involve code movement. I mentioned that basically this part of the process where you allocate and assign registers and want to generate code gets complicated, because once you assign the registers, then registers being fixed, naturally you cannot move your code around. So if there is a loop invariant inside a loop, you cannot move that out and so on. And if you want to do the instruction scheduling first, then you will have naturally issues of the registers may not be optimized. And we had discussed that a good strategy is to do instruction scheduling with certain symbolic registers, and then do again a global optimized allocation, and based on that you do a rescheduling and so on. You have to kind of do it in loops. But here I have assumed that there is no code movement that we will do. So it is kind of a one-pass process where we have optimized for registers and generated the code. For simple code, this itself will generate quite a nice code. So finally, when this is you have the control flow graph, so your code is in terms of this graph, but finally you need a linearized code, right? Your final code is a linear structure with conditional and unconditional jump. So for linearizing this CFG, you'll have to do a traversal on this CFG, and you will have choices of whether you take the left child or the right child, and based on that, different codes will get generated. Now, few things may be observed here while you do this linearization. Let me go back one step. Specifically, look at block B2, which has its last statement is a conditional jump. The statement 102 is R5 less than R3, go to 106. Right. Otherwise, you go to 133. Right. This is what I originally had. Now, what I have done here is I have flipped this condition. I flipped this condition because the reason I did that, and generalizing it is not trivial, but not very difficult either. What I have done is a choice that more often you will take this branch 206. Right? The more often you will go here, right? Because that is the basic loop, and less often you will. I mean, only once you will go to the return. So if you have, I'm going to the previous slide. If you have this condition check, then what you are saying is block 12 is on the fall through of your block 2. Whereas this is a jump out. Right? So instead of doing that, because more often you will actually not be taking this return, you will take this only once. I did that change. This is again in the back to the next slide, where I flipped this condition. So now B4 becomes my fall through. So you can see on the yellow part here, after B2, I come to B4, and only when this condition is satisfied that I go to B12, which is the return. Similar things have been done in this here. This is basically deciding on. So, for example, if you question as to what is the heuristics that I'm using? The heuristics that I'm using is, since we have nested loops, so if I'm continuing on the loop body, I want to bring that on the fall through, because more often I will get a condition which satisfies so that I continue in the body of the loop, then I go out of the loop. In the earlier conditions, mostly the body was not on the fall through, but exit from the loop was on the fall through. So using that heuristics, so you can see I've marked the fall throughs here. So I want to make that if it is in the body, then primarily put it in the fall through and flip the condition accordingly. So certain 102, 109, and 118 have been flipped in that way. So based on that, I can now linearize the code. So this is a change prior to your actual linearization process that you do. And as you linearize the code, for example, another that you should observe is in here you have B11, which ends with a go to B2, right? So what I expect to do is to actually put it on the fall through. So B11 has a fall through to B2. So if I have that, then this go to is not required. Go to at 105 is not required. Similar fall through case exists for B9 also. So as you can see that when you linearize the code, you are also kind of managing the control flow, right? So that there is a Traverse CFG managed control flow. So you are trying to do it with little kind of smartness so that you can minimize the jumps in the code, which is also a kind of nice optimization. So with that, as we linearize, we have B1. Now you have to remember that at this point, when we started, we had assumed that the value of n, the number of elements, and the array itself was known. And they have been allocated registers. Let me go back. This has ARR and R2 is been allocated for n. So this is what is not shown in this code here. It comes from the assumption we had made. So these two red lines are loading the initial value of ARR, the base address, and the value of n into R1 and R2 respectively. Then you have block B1, which is straightforward. Then R5 store all this. So go to, then you have go to B2. Right? This is, here is a direct arrow, but remember, note that this is not fall through because for linearization, I have allocated B2 much later. So you have a go to B2 where R5 has I. Now, after, so once this happens, once you put this go to, kind of your code has a break, remember, right? Because it is an unconditional code. So you can put anything after this, to which obviously there will have to be a targeting to come. So we have again on, if you go to check B2 here, you go to B2, then you go to B12 gets linearized in this part. So you can see that you may not be able to linearize in a simple pass to do that. You may put them into different arrays and then merge them as needed. Now, when you have go to Now from B4, again you need to come to B5, but that is not a fall through because of if you had a fall through, it would have been to B12. So you have to put B5 after B1 here. That's just a choice. So B5, then you go to B5. You have this condition at 109, which of which the fall through is B7. So after B5, you put B7. B7 has a fall through to B9, so you put B9. So kind of with this fall through, you are trying to find a long linear code so that no jumps and all that will be required. Obviously, the conditional ones will be there for taking you out of the inner or outer loops, or taking the two cases of the if statement that you have. So after this, you have B9. After B9, you have B8. And B8 has a go to B5. So you have a go to B5 where you're going back. So you have again the second segment, which is done out here. You are left with this part. So you put B11 after this, and finally the B2. Okay. So once you have got this code, then you can again do a DFA for the load store. Here, you can, it's a simple code you can do by simple tracing also. For example, let us say that what does B11 has? B11 has R5, which is loaded with IA. Okay? R5, which is loaded with IA. Now, where does the control in B11 come? It comes from B5. So if you see B5, you have loaded IA into R5 in B5. So it is that is live at the exit of B5 because R5 has not been changed. So when you come to B11, so B5 you are loaded, you get this condition, you come here. When you come to B11, then you have a load optimization issue, that it is already loaded, you are trying to reload it. So obviously this second load can be always removed. So it is a load situation. Similarly, let us consider here from B11, you are going to B2, which is a fall through. B11 to B2, which is a fall through. So we fall through here. So B11 has stored the value of IA. Okay. Stored the value of 5 into IA. Stored the value of R5 into IA. And then you go to B2 where you are loading this. So as you can see here, you have stored and then immediately you load. So you have a store load redundancy. So naturally, you will need to store the value for future use. But this second load is not required because R5 already has that value of IA. So you can also remove this second load. So once you have done that, you can see that with 6 resistors, you have a moderately nice code that have got generated. So again, just to remind you, the steps are assuming that we are not doing any code motion or stuff like that. The steps are generate the 3-address code array, then optimize it for peephole, for common sub-expressions locally and globally, and compute the liveness information. Based on that, do a global register allocation depending on the number of registers you had. And for the spill code, you will have load stores inserted. After that, you rewrite the code using the registers that have been allocated. And then for linearization, you first check that if fall throughs can be maximized in the code. Right. So this does not guarantee that you will always have a better choice, but this is a good heuristics to take, that if I maximize on the, so this is, I mean, more formally, this is done by computing the branch probability. At every point you can compute what is the branch probability. Now, that you cannot often do without profiling the code. So in formal terms, this is done by generating some code, then actually execute it for a set of sample data. And as you execute, you compute the frequency with which the different branches of the CFG are taken. Okay? You keep on collecting that profiling data. So after a while, you will have a good amount of data to give you the probability of different branching with typical data. So you can use that. And while you are doing a branching, the branch which is more likely, more probable, assuming that they are not kind of almost equal, then it is an arbitrary choice. But in terms of particularly loop body and loop exit, you are expected to see that the loop body will have a higher probability than the exit. So try to put those on the fall through by flipping the conditional go-tos appropriately. And once you have done that, then you take the longest chunks of fall throughs, because this is your sub part of the linearity that you have, like you had here as B5, B7, B9, B8. Similarly, here you have B11, B2, B4, like that. So these are the two main chunks. You put them one after the other. Then you stitch the other blocks with the no fall through. And that will give you a working linearized code on which again you can do a DFA for the load store, and you can remove the redundant instructions based on load or store load situations. So this is a simple scheme. I just worked it out for one moderate example to show you that even this macro-based simple scheme, with the use of optimizations and some additional heuristics like branch probability, can give us a fairly moderately good code. Of course, we will see subsequently that this code itself can be further optimized quite a lot when we go into loop optimization. But at a basic level, this is a pretty good working code that you can get to. So before I move on, let me go back to you and see what are your questions.
Sir, you were mentioning about like automatically you're going to retarget code given specifications of the target system.
Right.
But like, wouldn't that necessarily generate suboptimal code?
It it not necessarily it will, because as he is saying that see in the translation process, everything is in terms of an abstract machine. I think of it in a different way. Say, when you are in the front end, you are using representations which are closer to the language. That is why you have the parse tree, annotated syntax tree, and so on. When you are at the back end, the translation is basically between different abstract machine models. C address code itself is a machine, right? You agree to that, right? Three address
Yes, sir.
code is a virtual machine, right? So what is being said that if you can represent your processor as a virtual machine, which it actually is, the only difference being that it does have a physical realization on which you can electronically execute the code. But it is like a three address code to, I mean, one virtual machine code to another virtual machine. Right? So once you have done that, again, you can go back and do some of the optimizations that you did with the DFA. I was showing you here that we have done this, translated into with the registers, and I'm saying that that is my virtual machine. Earlier, my virtual machine had variables, this, that. Now my virtual machine is just 6 registers and these instructions. So that if you directly go to say x86, you'll be able to write an assembly by the side of each one. I mean, it's almost uniquely you can write an assembly. And then I did a further DFA to optimize load store. So it is not that if you just translate, you always have the best code. But you may want to do a series of optimizations after that. Now, what you're asking is a very, 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 very important question, I would say. So I will just step aside and answer that from a different perspective. If we historically see, because now what you have are primarily what we call the RISC architecture, reduced instruction set computer. Now, why is it RISC? What is reduced? Where is it reduced from? For decades now, we have that kind of processor, which primarily says that there are only few types of instructions. Either you load, or you store, or you do an ALU operation with registers, or you do some checks and do, or without check, do conditional, unconditional jump. Right? Now, so what is the genesis of this reduction? The genesis of this reduction is CISC, which kind of got the name more from the RISC. In the earlier times, the processor designers used to design instructions which are very, very smart. For example, you have seen here that for every 3 address code, or for many 3 address code, we are having to write a macro. Now think about in the processor abstraction, if this macro is micro coded, you know the micro instruction, which is the instructions that go on in the hardware to realize the assembly instruction that we see. Okay? So I can microcode that entire thing and make it one instruction. So I'll say that I have A assigned B plus C directly. There is one instruction which does that. Even more complex things like indexing an array and going over it. I'm adding a constant to all the elements in the array. I can have an instruction for that. So if I have these instructions which are actually not macros in the assembly level, but they are macros in the microcode level, naturally my efficiency would be a lot better because I'm doing that entire thing in hardware already solved, optimized at the design time of the hardware. So these processors used to have a huge instruction set, lot of complex instructions to help optimize the code much better. Now, so now I have an abstract virtual machine, which not only has these simple instructions, but have all these very, very optimizing instructions. Now, after a decade or so of having these kind of processors, when people went back and reviewed that, well, we have done so good instruction design in the processor, but let's see how our code is actually doing. what was found was appalling. That hardly any computer, any compiler used those smart instructions. Because of the simple reason is, writing an optimizer to make the proper choice of these complex instructions to take their benefit turned out to be so complex, because obviously all of these, whatever way you formulate, all of these are going to be hard problems. So they became so complex that the compiler writers took the easy way out, that choose the simple instructions, translate in terms of those, optimize them as much as possible. And it was found that there were processors in terms of which about 80% of the assembly instructions were almost never used by any compiler. So that gave rise to this whole thought process that, do we really need so many instructions? What is the point of having those instructions? It's hardly very few people are going to write code by hand in the assembly level. Okay? It will always be auto-generated. So then, do we really need so many instructions? So that gave rise to that whole philosophy of reducing the instruction set. And that is why RISC happened. And when RISC happened, since you chose to use a reduced instruction set, you also chose to do a lot of, simplification in the hardware architecture of your processor. For example, you made it very simple for all those complex micro instructions that you had earlier for complex instructions in the assembly, all those micro codes. You do not need those kind of processing and so on. All that you are saying, that let us go back to, the founder's model of von Neumann. All that you can do is to load, store, compute. And then, because you have a linear representation in the memory, you need chunk. With that, you can do everything. So what was possible is two things happened. One is, as you reduce the instructions unnecessarily available in the hardware which are never used, that redundancy was removed. As you reduce the instruction, your hardware becomes simpler to design. As you reduce the instruction, you necessarily made a simpler architecture for the hardware. So your simple instructions, which you will have to use more number of times because they do only small things, they themselves became a lot more efficient. And you move to this whole philosophy of have a small instruction set, each instruction doing possibly only one task, or maybe at most two, but not too many things with, accessing hundreds of memory locations, updating them. Those kind of instructions were all done away with. They do come back in a different context in other kind of processors. That is a different story. But in our all regular processors, it is, whether it is explicitly said or not, it's driven by this RISC philosophy. So for compiler writers like us, now the target is to design strategies for this kind of a virtual machine. So our virtual machine has become very simple. It is RISC. It is primarily a load store architecture. Let's say there are some variants, of course. Primarily a load store architecture. These are the 4 or 5 types of instructions we have, and we will choose based on that. So even though you have processor variabilities, like between x86 32-bit and x86 64-bit. Let's just take these two. We understand that mostly. What will be the difference? The main difference is the representation of the basic data type. And accordingly, you have some additional instructions. Otherwise, x86 64-bit will in a way have all the 32-bit instructions. So you can, as you do for the 32-bit, it is just becoming another model of 64-bit. And you expect, because the architecture is same, mostly same. Don't take me literally. Architecture is mostly same, because as you increase the basic size of the basic data type, certain things like addressing and all will obviously change in a certain way. But in an abstraction, they have the same architecture, same set of instructions, but only specificities are different. So when I'm writing the code generator, if I can represent this specificity in terms of a, abstract specification, and use that as my guideline, then I will be able to generate a moderately good code in that virtual machine. And then again, in fact, with retargeting, oftentimes what the compiler writers do is they do a retargeting of the basic translation. And then they may have another 1 or 2 passes which are specific for that architecture, which kind of come in if you go to a higher optimization level in your code. It will normally not.
So that's the thing that is used,
right? So I had to tell a long story, because that is what the whole reality stays in. So when you go to higher optimization, it is not only that you are targeting to look for deeper analysis to find out more idiosyncrasies of the code, but you may kick in a lot of processor specific stuff that comes in. So what happens in the process that if you did not do this specification based modeling, then for every processor you would have required to write the whole backend. You are increasing the reusability of the backend. And as you will see that your Intel processor and AMD, they are said to be instruction compatible, but they are not. In general they are, but not in the specificity. So you'll have to make differences and take care of those. So that is the issue of retargeting, which is by itself a very deep subject to study, because every time you generate a compiler version, you have to retarget it to possibly, these days it's at least 10, 20 processors on which you are retargeting. I think that kind of gives you an idea about the whole. It does not give you the solution.
So the processor specific things are shifted towards then, so that we have processor independent stuff as much as possible.
Yes, and the basic thing to understand is the way we have described. We have always been talking about quad 3 address code, but it's actually a virtual machine. So every instruction or the basic data flow dependencies you are talking of, they are not specific to 3 address code. They are specific to any symbolic representation and with computational items. So in your assembly code, whatever that assembly is, you can again go back and do a lot of optimizations. So mostly up to the retargeting, mostly we'll do the logical optimizations that are possible at that level. Now, even the processor architecture may tell you that in this particular situation, this instruction works very well. You may want to do that in a further optimization level. And many compilers actually do that. Okay. Any other? Welcome. Any other question, friends? Did I put you all to sleep with this detailed discussion? But when you're doing your architecture course also, right? Or you are done with it? You're doing it this semester.
So we are doing it this
semester. So I'm sure this risk issues and all these. Obviously, we are not considering a lot of other processors in this story. For example, the vector processors, the parallelizing compiler issues, and so on. So there are several such. So vector processors do have certain, complex instructions for specifically for vector operations, and therefore many compilers or many designs need that you use a library for using that vector instructions, so that from the front end itself, you could pass some information that this needs to be vectorized. That is, don't treat this array as an array. Use it as a one unit vector, which you can target to the vector instructions. So that there are instructions to just add two vectors in a single instructions, which is very common when you do vector algebra, matrix algebra, and so on. So there are a lot of extensions to this. We are having to stick to very general purpose and simple processes and simple strategies for the current purpose. I don't know how much time will be there at the end. If there is one or two lectures available, I'll try to talk about some of these other issues that are involved in other kinds of processor architecture. But always remember that when you design an architecture and when you design a compiler, it has to be very much hand in hand. That is the lesson that first 30 to 40 years of computer science has taught us, that you cannot go independent on this. You have to design the processor for the compilation, design the compilation for the processor. Otherwise, you are not going to do a great job. Okay. So, any other questions, friends? No. So let's take a break for 5 minutes, and then I'll continue on the second skill. So we will meet after 5 minutes. Okay, let us get back. We now move on to a different scheme, which we refer to as scheme B. And this, in a way, will lead to an optimal algorithm also, but it is not optimal in time. It is optimal in the length of the code. We'll see that. Now, to implement this algorithm, we make use of two data structures. One is called the register descriptor. A register descriptor is which tracks what are the values that are available in a register at any point of time. So it is like register and variable name pair. A register may contain values of multiple variables at the same time if they are all copies. Like I copy A to B. If A was in register R1, then actually I don't need to do this copy. All that I need to maintain is B is also in register R1. Right? So that in a way, this representation itself could optimize certain parts of the code. Okay. The other that we have is kind of the reverse, where we say that it is an address descriptor. In the address descriptor, we have a variable and the location where the variable is available. A single variable may be available in multiple locations. For example, I have done a load. The moment I have done a load, before the load, the variable was available in the memory. It had one location. After the load, the variable is available in the memory as well as the register into which I have loaded it. But after that, if I change that variable, say I make some assignments to it, then it may be available only in the register, not in the memory anymore, because the memory copy has become dirty. It has become old. Till I store it. When I store again, I have two copies, one in register from where I have stored, and one is the memory location where it is available. And it is possible that it will have more than two locations also. So this two data structures, please keep in mind, simple data structures, but they will be very useful in tracking the code generation process. Right. So our basic strategy for this simple code generation is to leave the computed result in a register as long as it is possible. That's the basic premise of optimization. So we store only at the end of basic block or when that register is needed for another computation. We may run out of registers and we need. So on exit from a basic block, we will store only the live variables which are not already in their memory location. We will have the live variable information that has already been analyzed. And the address descriptor will tell us whether the value of that variable is already in the memory location, because then the address descriptor will have that memory. In that case, we do not need to store it. Otherwise, we will need to store it. But if the liveness information is not known, if that analysis data is not available with us, then we will assume that all variables are live at all times, and we have to store whatever was computed in that basic. So what are the sample codes again? If A is assigned B plus C, then if B and C are in registers R1 and R2, the address descriptor will tell us that. Then we can generate add R2 R1, which has a cost of only 1, as we have said, and the result will be in R1. So this will be legal. So what is happening with this? With this, R1 had B and R2 had C. When I have added R1, R2 into R1, my value of B is got erased, because after this, R2 will have the value of C and R1 will have the value of A. Right? So this is legal if B is not live after this statement. Otherwise, we are losing the value of B and we will have to load it again. Now, if R1 contains B, but C is in memory, right? In this model, we are assuming that we can operate directly with memory. Then we can do add C R1, where the cost is 2, because we are using the address of C. So it is 2 words and the cost will be 2. And the result will be in R1. That means B gets invalidated. If otherwise, what I can do, I can load C into register R2, bring to the first case, and then add R2 to R1 and keep the result in R1. This will have a cost of 3 because load is 2, add is 1. So cost is 3. The result will be in R1 and B will get invalidated. So again, it is legal if B is not live after the statement. And this may be attractive over the first one, even though this has a higher cost. But this may be attractive if the value of C is subsequently used, because it remains in R2 after this instruction, and therefore it can be reused. Okay? So these are some of the basic observations that you can keep in mind. Now, having said that, we will compute a new set of information in a data structure called next use. This information will be used in code generation and register allocation together. So what is next use of a variable? The next use is basically it's a part of the def use chain, but it gives you that if I have quad I, where the variable A is assigned, that is defined, and there is a control flow from I to quad J, where A is not modified, there is no assignment to A. And in quad J, A is used. There is a right-hand side, A is used. Then I will say that the value defined in I is being used in J. So that is the next use of A. So while we compute the next use, we assume that on exit from the basic block, all temporaries are considered non-live. Because temporaries are only for temporary computation, so they should not remain live. And all programmer-defined variables and non-temporaries are live. Each function and procedure call is assumed to start a basic block, which is trivial. Now, how do you compute next use? So the next use is kind of, it's a def use part, and it's kind of a restricted definition of liveness. So naturally, it will have to be computed on a backward scan on the quads in a basic block. So because you know at the end of the basic block what is live, so you know their possible next use, and you come backwards from that point, and this information can be stored annotated on the symbol table itself. Right. So this is a next use information which is important. So let us just try to take an example to see how to compute this. So here is a sequence of instructions. These are the variables. Programmer variables are A, B, and product. You can easily understand that this basically is an inner product being computed between two vectors A and B, and this is kind of a Fortran example. So where the array indexing is from 1, so you are adjusting for that. Now, These are the annotations for the next use. We write NLV to mean not live. We write LV to mean live. We write LU to mean last used. When was the variable last used? We write NU to mean next use. We write NNU to mean that there is no next use. And we write LU0 to mean that there is no last use. After definition, use has not happened. Okay. So now to compute the next use of these variables, we'll go backwards. So I start from instruction shown at 11. If I is equal to 20, go to 3. So there is variable I. So it's a program variable. So I assume it to be live. So I say it is LV. Last use is in 11 because in this instruction it has been used. And no next use is known. So I write NN. I come to the previous one. So as I come to the previous one, I again have I. So I has to be live because it has a, so its next use is the last use that we have here. So this next use is 11. It has been used here. So last use is 10 and it is live because it has a next use. I go backwards again. Now I have T6 and prod. Now coming from the end, I have not yet encountered prod so far or T6 so far. So both of their next use is not there. So no next use. Both of them are used in this instruction. So last use is 9. And prod being a program variable is considered live. T6 being a temporary is considered not live. So at present, I have in the next use tuples for prod, T6 and I. Remember that. As I go backwards, I have T3, T5 coming in, which did not appear in the current list. So T3 has no next use, T5 has no next use, whereas T6 appears here, which has a last use in 9, right? LU9. So the next use of T6 is next use 9. T6 is defined at this point, so it does not have a last use. So last use is 0. And T3, T5 are used here, so their last use is 8, the current instruction. And all of them are temporary, so they are not live. Go back. So now we have T6, T3, T5, prod, and I. There's 5. Now, as I go back, I have T1, T4. They are not in this list, so their next use is not there. I'm sorry. Last use is this instruction, so 7. They are not live, clearly. T5 is defined, so LU is 0. And T5 has a last use 8. So the next use of T5 is 8. So I have T5. So I go back again. I have T4 with last use 7. So next use of T4 is 7. It is defined, so last use is 0. And I have B, which being a program variable will be live. It has no use so far, so next use is not there. And it is used as an instruction, so LU6. I go back to instruction 5. T1, T2. T2 has not been used so far, so there is no next use, only last use is the current. T1 appeared here in 7. So T1's last use was 7. So T1's next use now is 7. Both T1 and T2 have last use 5, the current one. T3 is defined LU 0, and T3 had occurred earlier in statement 8 with LU 8. So the next use of T3 is 8. I go back in here, T2, it has a last use 5. So next use is 5 here. Defined here, so LU 0. A is live. A is used here, so LU 4. And there is no next use because A has not occurred yet. Finally, the first instruction at 3. So I is where? Here. Last use is 10. So the next use is 10 here. It is defined at this point. It is used at this point. So LU is 3. Program variable, so it is live. T1 is not live. Defined here LU 0. And T1 had a last use 5. So its next use is 5. So in this way, this is just a simple example to show that in this way we can compute the next use information. Okay, so that is so we have 3 things done so far. One is we have the register descriptor data structure, we have the address descriptor data structure, and we have the next use information annotated on the symbol table. Now we will deal with the actual, core of the algorithm. So we will here deal with one basic block at a time. And we assume that there is no global register allocation that has been done. Here, the register allocation and code generation will be done together in a way. Okay. So let us see how we go about doing this. So A is assigned B operator C, which is a generic form of any instruction that you have. Now, we will need to find a location where this result of B operator C will be there. So we design an algorithm called getRegister, or a function called getRegister, which will give us this location. We will go into the details of what is getRegister, but let us for now assume that getRegister returns me a register, if possible. Otherwise, it could return me a memory location. So this getRegister is what is the location L that I get where this will be B operation C will be complete. Now, so that is the target. That is where the value of A will finally be found. Now, the question therefore is next question is where is B? Right? Unless I have B, so B can be found in the address descriptor of A. Right? Is it address descriptor of B? We have the address descriptor, so that will tell us what are the locations where B is available, because B must be available, otherwise this computation has no meaning. So if there are multiple, then we will prefer a register for B primed if it is available in memory and register as well. Otherwise, if it is in register, we obviously take that. If it is only in memory, we do not have a choice. So we will generate a load of B primed into L if B is not in L already. It is possible that B may already be in L. If it is, then we do not need to do the generate. Otherwise, we will generate a load from B primed to L. Now, remember, see one thing here, that the protocol that we are taking is the value of the left operand will reside at a location before I do this, execute this instruction. It will reside at a location L where the result will be finally computed. Right? Because that is the location L is the location that I have chosen to perform this. Just hold on for a second. There's someone at the door. Please hold on. Sorry, I'm back. So we find out the place B primed from the address descriptor of B and choose to take register if there is a choice between register and memory, and then generate a load to the target B prime to the target location if it is not already there in the target location. Now, next is you have to find C, the right operand. C prime is found using address descriptor for C. Again, if C is in register, you will prefer that. And once this is done, then we will do an operation of C prime L. So this will, L already has B. So C prime operation C prime del will actually do B operation. C, the left operand being in the target. And after this operation, L will represent the final computation done for A. So to give effect to the assignment after the operation, all that you need to do is to update the descriptor for L and the descriptor for A. For example, the descriptor for L earlier had B prime, earlier had B because L was carrying B, that is what we guaranteed. Now it will have to carry A, and L will now be available. A will now be available in A. So A descriptor of A will be updated with L. Now, if B or C have no next use, then the descriptors can be updated to reflect, will be updated to reflect this information. Right? Next use we already have, right? Because then that will actually make it simpler for the getReg function to give us a register. Right? So if the getReg function can give us the target location where the computation has to go, then this will be the simple strategy to generate the code. So what is the getReg function? So getReg function is called to give us a L given that we want it for B operation C. So what getReg does, if B is in a register, we can find out from its descriptor, say R, and that register has no other name. So here I use that just descriptor of B, and here I use the register descriptor of R. So if B is in a register which only has B in it, and if B has no next use, B is not live after the block, then I will return R as a value of N. The rationale is simple. B is in a register. Now, if R holds another name, then naturally I cannot use that register because I know that it will be overwritten by the value of B operation C as computed. If B has a next use, then also I cannot use this register because I will lose the value of B. If B is live after the block, I would not do it because I will again lose the value of B. But if this condition satisfies, then the register R can be returned. And in that case, as we have seen earlier, in the earlier last slide, that in that case, loading B into R will not be needed because B is already in R. Now, if that condition is not satisfied, most cases it will not be satisfied. So failing one, return an empty register. So if we have an empty register, you return that. And if we return an empty register, naturally we'll have to load it with the value of B after you go back from the getReg function. Now, if there is no empty register either, so now what you'll have to do is necessarily do a kind of spilling, right? Because everything is occupied. So you'll have to find out something else. Now, if A has a next use in the block, or if B operator C needs a register, because it is, I mean, many operations necessarily need a register, like indexing operator and so on. Then you will do this steps to spill. So to spill, what is that you need to know? You will need to know which register you want to spill, because all registers are full. So anything that you spill, you will have to store its value back to the memory. So it is again a hard problem. I mean, if you want to find optimally as to what register to spill, you will not be able to solve it in polynomial time in general. But a good heuristic is to find an occupied register whose contents are referenced farthest in future. Every register has its descriptors, so it has the variables. So you see which one has the farthest reference. Right? So it means that that register will have to carry the value of that variable for the longest period of time amongst all the registers. Right? So it will be okay to compromise that and use that register. Or you can use in this way, or you can use a heuristic that the number of next use is the smallest. Every register has some variable. So you see what is the next use of this variable. And whatever is the smallest next use, you can use that. I mean, these are all heuristics to just hope that in future the load store will be less. Once you have made that choice, then you have to spill that register by generating a store instruction, move R to memory, which is store. Mem is the memory location for the variable in R. So, and that variable is not already in memory. Right? If that variable is already in memory, then you have a happy situation because you don't have to generate this store. You just need to update the register and address descriptor. Obviously, you have to update the register descriptor because after this, you want that register to have the value of, you want to designate that register has does not have that variable anymore because you are going to release it by the getReg, and the address descriptor of that variable will have to be updated because it is no more in that register. It will only be in that memory. So this is what you do if this condition satisfies, that if A has a next use in the block. But if A is not used in the block, or in this process you do not find a suitable register, then you will have to return a memory location for L. This will hopefully happen sparingly, but this is this fourth condition is given to make sure that get register at least returns you something. So this is the sample. So again, reminding that B is in a register which does not hold a name. B has no next use. It's not live after the block. You will return that register. Otherwise, you will return an empty register. Otherwise, you'll check if A has next use in the block or B and C needs a register, and you'll spill where you use one of 2 or 3 different choice of heuristics. And after spilling, you update the register and address descriptor. If none of these happen, then you return a memory location. So using that, let us generate a code which is very, very simple. So we assume that T, U, V are temporaries. They are not live at the end of the block. And W is a non-temporary, which is live at the end of the block. And we have 2 registers, register R0 and register R1. So T assigned A star B. So what will it do? So what is the register descriptor and address descriptor at this point? You do not have anything in the registers right now. Everything is in memory. So if you call the get reg with A star B, A is not in a register. So you will come to the second condition, which is getting an empty register. So you get an empty register R0. So you'll have to load A into R0. And as you load A into R0, along with that, you will so you have the variable in R0, then you will multiply B to R0, the right operand to R0. So the result is now what is T. So R0 now contains T. T is in R0. This is a register descriptor and address descriptor. Now you have A plus C. Again, as you call get reg, A is not in a location. It is in a register. It is in memory. So you return an empty register condition 2. You return R1, and you load A into R1, add C to R1, and that result that you get in R1 is actually U. So you write U, R1 contains U, U is in R1. Now you have V assigned T minus U. So as you do that, you go to get reg, and what does get reg give you? Get reg tell you that T is in R0. T is in R0. It is in a register. So by condition 1, you will return that register because T is temporary. It is not live. In that, after this, it has no next use. So T is in R0. So you return R0. Then you try to find where is U. You find U is in R1. So you have got T in R0, U in R1, and you subtract R1, R0, and the result will be in R0. Okay. So R0 now is updated from T to V, and V is in R0, T is not anywhere, it's lost. You don't need it. Similarly, you have V star U after this. So V is in R0. So that will be returned as the target register. U is found in R1. So you simply do a multiply of R1, R0, and the result will be in R0. So R0 will contain W now, and W is in R0. And we said W is a non-temporary, live at the end of the block. So we have come to the end. So now we have to write back R0, W. So we store R0 to the address location W. So W is in memory, which is this. So using this, you can very simply generate a code in this. It's not going to be optimal or often very good, but this is a simple way to keep on reusing the registers, keeping track of the next use and live information. So you will usually do a decent job by doing this. Now, so that was a simple way to do scheme B. Now we will tweak on this to generate an optimal code. This algorithm is by Sethi and Ullman. So this generates the shortest sequence of instructions. So it is a provably optimal algorithm with respect to the length of the sequence. So we have been trying to minimize time, but as you can see that this will actually minimize the length of the code. In a way, it will minimize the memory. And then your basic heuristic is if it is shorter in length, then somewhat it should be more efficient. But this is actually not provably optimal for the time, but it does well for the time. And it is particularly good for expression trees. So it's at the typical basic block level. Now again, what is the abstract machine that we are assuming here? Abstract machine, we assume that all computations are carried out in registers. That is, the result will have to be in the register. And instructions are of the form that you have seen. Operation RSRT or operation MSRT. That is, the left operand could be an address, could be a register or a memory, but the result will always have to be in the register. The key point to note, the assumption here is that always compute the left subtree into a register. When I said we are talking about an expression tree. So you have a left operand, you have a right operand, and left operand naturally will have another expression tree below that. So there's a left subtree, and right operand will also have that. So always compute the left subtree into a register and reuse that immediately to do the computation. Now this goes by two phases. In one phase, we label the expression tree with the least number of registers that we might need. And the second phase is actually for generating the code. Okay, so first, how do we label? So we label each node of the tree with an integer. And without loss of generalization, we assume that it's a binary tree. Right? That is the label is the fewest number of registers required to evaluate the tree with no intermediate stores to memory. We're trying to see how many registers I need at the minimum to evaluate this expression tree if I do not want to store any intermediate result. So, and remember, going to the previous slide, remember that always computes the left subtree into a register and reuses it immediately. That is the basic assumption. So for a leaf node, if n is the leftmost child of its parent, then level of n must be 1. Because it is the leftmost child, it is a leaf node, so I need one register to represent its value. But if it is not the leftmost child or the left child, so to say, for binary trees, then the level is 0. Right? Because I'm not going to I'm not going to use a register to store it. I will directly use it in the computation of them. Now for an internal node, I have 2 children. Now, so I have 2 subtrees. So the level of n is the maximum of L1 and L2. L1 is the minimum number of registers to compute the left subtree. L2 is the minimum number of registers required to compute the right subtree. So if L1 is not equal to L2, that is either L1 is smaller or L2 is smaller, I will need the maximum of that. But if they are equal, then I will need one more register, the register where the result has to happen. So because I have done I'm not explaining it right. Forget this. I'm not explaining right. So I need that one more because I'm doing the left subtree first, and then I want to use it immediately. So after having done the left subtree, I have to compute the right subtree. So left subtree required L1 number of registers, and after it is done, I will need one register to remember the final value of the left subtree, the root of the left subtree. And to compute the right subtree, I need L2 number of registers. So while I compute the right subtree, I cannot use the register where I have kept the value of the left subtree. So I need one register more than L2. So this is L2 plus 1 or L1 plus 1. But if they are unequal, then I will need the maximum of these two, because what is the intuition? Intuition is simple. If they're unequal, then one is smaller, other is larger. So what I'll do is I will compute first the larger subtree. After having computed the larger subtree, let's say L1 is less than L2. Then larger subtree again is not a correct statement. The subtree that needs more number of registers. So let's say L1 is less than L2. So I will compute the right subtree first, getting the value. So it will require L2 registers to do that. After it is done, the result of the right subtree will be retained in one register. Then I will do the left subtree. Now, since L1 is less than L2, L1 at the maximum can be L2 minus 1. So even after I have kept the result of the right subtree in one register, I would still have L2 minus 1 registers available to comfortably do my computation of the left subtree. Similar logic will apply if L1 is greater than L2. So in this case, if they're unequal, it is the max. If they're equal, then it is one more than each one of them. So just showing you the labeling these N1, N2, all these are basically operators which will operate on this. So they're just shown as nodes, and the leaf ones are variables A, B, C, D, E, F. So if I see here, this is the leftmost child, so it gets 1. Leftmost child gets 1. Leftmost child gets 1. Right child gets 0. So this is a leaf level. What happens at N1 is the left number of registers in the left subtree and number of registers required for the right subtree. They are unequal, so the max is taken, which is 1. So similarly, in N2 it is 1, in N4 it is 1. But in N3, N1 and N2 both require 1. So they are equal. So N3 will require 2. In N5, they are not equal. So it is a max. So N5 will require 2. So we say that if this is the structure of the expression tree, then following our convention, we would be able to evaluate this tree using 2 registers always, but not less than 2. So this is the labeling. So you assume that the labels are all available. Now, to generate the code, we again assume that there are 2 data structures. two stacks. One is a stack of registers. So if I have R registers, then I have a stack of registers R0, R1 up to R minus 1. It is called the R stack. And there is a T stack, which is a stack of temporaries, which is infinite. T0, T1, as many as you want. Now, why do I need this stack of temporaries? Very simple, because I've already seen through this leveling that there is a minimum number of registers that I need to compute an expression tree. Now, my actual available registers are maybe equal to that, more than that, then I'm fine. I will not need temporaries. But if it is less than that, for example, for the previous one, let's say for this tree, if my R, small r is 1, that is, if I only have one register, then obviously I cannot generate the code using only registers. I will need temporaries. So the temporaries that I use, and when they are done, I get them back, is maintained in the stack of temporaries, T stack. So I call to GenCode. GenCode is a code generator, which takes a node as a parameter. It's obviously a recursive function. GenCode N generate code to evaluate the tree T rooted at N. And how does it do the evaluation? It evaluates in a way that at the end of the evaluation, the register stack, the top of the register stack will have the value. So top of the register stack will always have a register, will have the register where the value computed at this node for this node will reside. And the rest of the R stack, both are, so the value will be in top of register stack, and the rest of the R stack will remain in the same state as the one before the one. So before calling the gen code, there was a state of the stack. During gen code, that state may have changed. But when gen code terminates for n, then the top of the stack would be the result computed, and rest of the stack will be same as it was before the call. The last is a little tricky one. While you talk about stack, we talk about push, pop, empty, and top functions only. But here we provide a special function for this this stack of registers, R stack, which is called swap. What swap does is it swaps the top two registers of R stack so that I can always maintain that a node is evaluated in the same register as its left child. Because you will understand that depending on the value of the level, I might need to evaluate the left operand first and then the right operand, or the right operand first or the left, then the left operand. Now, if I do the right operand first, then I have done it, then I do the left operand, and the result of the left operand will be on the top of the stack. So therefore, I have a comfortable situation, because the result will be computed in the register where the left child is. But if I have to do the left operand first, then the latest one, the right operand will be done next. That is, the right subtree will be done next. So then the result of that will be the last one that I have on the top of the stack before I go into doing the operation at the next node. So I will not be able to maintain this basic assumption that the left child and the final result will use the same register. And for that reason, you use this swap function, which is special for this stack. Oh, it's time. So let me stop here. In the next class, I will discuss about the different cases of this algorithm. If there is any question, I can quickly take. Yes. Is there any quick question? Then I can try to answer. Otherwise, it's actually already time. I didn't try. Okay, it seems none. If there is any, just